Welcome, guys, to our first chapter dealing with the different phases of matter. First one we're going to start with looking at is gases. So we are beginning chapter 12, looking at gases and gas laws. Now this chapter is going to seem like a lot of review. That's because it is. It contains a lot of the gas law equations you guys learned from before. We'll take a look at a few new things that we have to be worried about. There's a handful of few new equations, but for the most part, you should recognize most of this from your first year chem class. Chapter begins talking about one particular property of gases, and that is pressure. Pressure is simply defined as the force per unit of area. We have lots of different units for pressure. The SI unit for pressure is known as the Pascal, which is abbreviated capital PA. A few units of pressure that you do need to be familiar with are ATMs, which is short for atmosphere. 1 atmosphere is equal to approximately 760 millimeters of mercury, which is also the same thing as 760 torr. 1 atm of pressure, which is basically at sea level, was defined as holding up a column of mercury 760 millimeters high. Another unit there, torr, is actually named after the scientists who first started doing experiments with pressure, Torricelli. So that's where that one comes from. A few other equalities. The 1 atm, same thing, is this. It's also equal to 1.01325 pascals. Actually, no, I forgot. It's actually equal to 1.01325 times 10 to the 5th pascals. Forgot that little part there. And that's the same thing as 101.325 kilopascals. So be familiar with some of these unit conversions. On your equation sheet, you'll notice different units that they're given to you and their conversions, so just be able to convert from one unit to another. Some equations demand certain units, and some constants demand certain units, so it's a good idea to be able to convert from one to the other depending on whatever the situation calls for. Okay, now we're going to move into the gas laws. It's pretty much where our chapter begins. Now the gas laws are, like I said, that's pretty much the same as what you guys have learned before. It's really good to know the relationship between the gas laws and the gas variables, the relationship between the variables. A couple things to note. First gas law we'll look at, Boyle's law. Okay, Boyle's law comes from the main idea is that, hey, gas is compressible. You can take a gas, and there's lots of empty space between gas molecules. You can actually crunch them down into a very, very small amount of space. Most of the gas in whatever room you're in right now could actually be condensed into a small enough container to fit in your pocket. But it's pretty crazy that, hey, it expands and actually fills up the entire space of whatever room you're in, as big or as small as it might be. Okay, Boyle's law simply states, in words, that the volume of a gas is inversely proportional to its pressure. Now this only is true as long as the other gas variables remain constant, and that would be temperature and moles, which basically represent the amount of the gas. So as long as you're not changing the amount of the gas and you're not altering its temperature too much, volume and pressure are inversely proportional. If you were to graph this concept, okay, as you guys did in your first year chem class, our pressure on our x-axis, volume on our y, graph would look something along those lines. Not a straight line, it's actually a curve. As your volume slowly decreases, as you can see here, the pressure doesn't change a whole lot, but then all of a sudden you really start to compress the gas and the pressure starts increasing exponentially. And your pressure rises as your volume really drops. But then you can't keep compressing a gas infinitely. It can actually compress all the way down. It'll start turning into a liquid. The molecules will get so close together they'll resemble a liquid. So the graph isn't infinite, but that's your general shape. Another graph to be familiar with, if we take our pressure, keep that on the x-axis, and we actually graph the inverse 1 over volume, you do get a nice straight line going through your origin there. I kind of missed it a little bit there. But you get a nice direct relationship. So that leads Boyle to develop an equation for both of these variables. And our equation is P1 times V1 equals P2 times V2. Inverse relationship. Okay, good law to know. Now another gas law we need to worry about is Charles's law. So Charles looked at the relationship between volume and temperature. He figured out that, hey, as volume increased, with an increasing temperature. But again, this is only true as long as you keep your other gas variables constant. Oops. I was going to write temperature. No, we're not keeping temperature constant. We're changing temperature. We're keeping the pressure. And we're keeping moles constant. So the amount of gas and the pressure, as long as those two things remain the same, as if you increase your temperature of your gas, the volume will continue to expand. This represents a direct relationship, so that leads us to an equation. A gas's volume and temperature is proportional to a new volume, an increase or decrease in volume with the corresponding increase or decrease in temperature. Now, this being the first time that we're mentioning temperature, it is important to note that our temperature must be in kelvins. For our gases and our gas laws, we've got to make sure that temperature is represented on the Kelvin scale, the absolute scale, meaning no negative temperatures. So smallest possible theoretical temperature is 0 Kelvin, leading all the way up to, well, infinite temperature. Quick little side note, I'll add it right over here. To convert to Kelvin, we take our degrees Celsius and we add 273 to it. So really simple conversion, and if we wanted to go back and forth, if we wanted degrees Celsius, we take our Kelvin, subtract 273, we get the same thing. So very good, handy relationship to know. I believe that relationship, the Kelvin and Celsius relationship, is actually on our equation sheet as well, although you might want to check that one out before assuming that it's on there. Okay, moving right along. We have eventually, these gas laws were actually combined. That's terrible. I can't even read what I just wrote. Alright, I'm starting over. I'm trying to write the word general. Alright, here we go. A little bit slower. General, that still doesn't look that good. Oh well, you can figure it out. General gas law is if we take both of those laws and combine them. Sometimes this is just simply referred to as the combined gas law. But if we combine Boyle's and Charles, we wind up with this very handy equation. And this is the equation that is on your equation sheet. You won't actually find Boyle's or Charles's law individually, and I'll double check that just to make sure, but in years past it hasn't been represented individually, but it's represented here together as a combined gas law. But it's actually kind of nice because you can see the laws in there, inside the combined gas law. If you'll notice, here is Boyle's law, our pressure and volume, right? If temperature remains constant here and here, it's not changing. So you can factor it out, and you wind up with P1 times V1 equals P2 times V2. Likewise, if pressure is not changing, if P1 and P2 are exactly the same, that drops out, and you wind up with Charles's law, which would be V1 over T1 is equal to V2 over T2. And you also get a really handy pressure and temperature relationship as well. Hey, if volume's remaining constant, if V1 and V2 are exactly the same, well, guess what? They drop out of the equation. You wind up with P1 over T1 is equal to P2 over T2. So it's kind of nice. All three relationships are represented right here within the combined gas law. The only thing that's missing is the amount of the gas. That's not actually there. So the amount of the gas, quantity if you will, and the unit we use to represent that will be moles. Quantity of the gas does not change. So remember that is keeping constant. Alright, so we haven't really involved our mole value at all, so let's take a quick look at how the mole factors into our gases. So let's look at a quantity-volume relationship. So now we mentioned the lovely scientist Louis Gay-Lussac. And he has actually done a lot of his gas studies at the same time that Amadeo Avogadro was doing his mole studies. Gay-Lussac actually held the record for going highest in a hot air balloon. He actually went up about 23,000 feet studying gases and what they could do. So he was actually quite the adventurer at the time, despite what some people might say about him, not mentioning any names. Anyway, so he studied numerous gas law properties, and he actually found out, he figured out what we now call the law of combining volumes. He actually discovered that at some constant, some given pressure and temperature, which I'm going to simply abbreviate P and T, he found the volumes of gases react in whole number ratios. Simplest example, if you have say 2 volumes, 2 liters, say 2 liters of hydrogen gas reacts with 1 liter of oxygen gas, it'll actually produce 2 liters of water vapor. If those numbers sound familiar to you, they should. That's actually the balanced equation for water. Those are the stoichiometric coefficients, which is actually what Avogadro came along and connected with Gay-Lussac's gas law information. Okay, and he actually developed what we call Avogadro's hypothesis. Oh, you know what? I should have capitalized his name. Avogadro, there we go. Avogadro's hypothesis. Okay, very simply states that, hey, equal volumes of gases don't forget, they have to be at the same temp and pressure. Contain equal molecules. Equal Run out of room here. You get the idea. Let me see if I can fit it in here. Molecules. There we go. Okay. So quite an interesting discovery that if I have 1 liter of one gas and 1 liter of another gas, no matter what the gases are, if they're at the same temperature and pressure, they have the same exact number of molecules inside whatever container that they're in. Example, if we have 22.4 liters, a magic number in the gas world, if I have that volume of gas, of any gas, and I have that at, say, 0 degrees Celsius, which is the same as 273 Kelvin, and 1 atm of pressure, standard pressure, that actually equals 6.022 times 10 to the 23rd molecules. And if that number sounds familiar to you, it should. That is 1 mole. How about that? So, that 22.4 liters means you have exactly 1 mole of any gas if you are at 0 degrees Celsius and 1 atm, which is what we consider standard temperature and pressure, which we abbreviate as STP. So a good relationship. The volume of a gas here is 22.4. If I'm at STP, which means 0 degrees Celsius and 1 atm of pressure, that means you have exactly 1 mole of a gas. I'm pretty sure you guys could figure out that if I had 44.8 liters at 0 degrees Celsius and 1 atm, I would have exactly 2 moles. So hey, double the volume, double the moles. So this actually led to what we call Avogadro's law. That the volume and those moles are proportional to each other. The volume of your gas, and I'll say it again, at constant temperature and pressure, is directly proportional to your moles. Proportional to the moles. Now let's go ahead and wrap up this lesson. With our combination of all of our gas properties into what we call the ideal gas law. Of all the gas laws that we go over, this one is probably the one most used in this chapter and certainly on the AP exam. We combine all variables. That variables looks awful. I don't like it. I'm going to rewrite it. Oops. I got rid of an L. There we go. Combine all variables. Hey, there we go. All right. So we wind up with all of our variables proportional to each other. We actually have to include a gas constant to relate all of our variables together, but we wind up with the ever popular PV equals nRT. A few things to take note is what these variables are. We have our P, which is our pressure. We have our V, which is our volume. N is going to be equal to our number of moles. T is our temperature. And of course, R represents our gas constant. Okay, and this one you do want to watch out for. Gas constants, the gas constant, can actually come in a few different forms. one of the forms that I 0.0821. This is the gas constant I generally try to use the most, mainly because of its unit. The units for this constant are liters per atmosphere over moles times kelvins. The units of the gas constant basically determine what units your variables need to be in. So if I'm going to use this constant in my gas law, when I solve for my variables, I have to make sure that my volume is in liters, that my pressure is in ATM, well, N is moles, so there's really no other unit there, and I do have to make sure that my temperature is in Kelvin, but that's pretty universal. Volume can come in all sorts of different other units, milliliters being the other most popular unit for volume, so you want to make sure you're in liters. And pressure, as we already started with, that can come in lots of variations of units. So you want to make sure you're either getting it to ATM or you're using an appropriate gas constant to use with whatever unit that you do have. Again, I'd stick with the 0.0821. I generally like thinking of my pressure units in terms of ATM. So that's the one I tend to use most. I tend to try to get my units there. I convert them to these units so I can use this gas constant. It's also the one I'm most familiar with and the one I have stuck up in my head. 0.0821 is going to be the gas constant that's represented on your equation sheet for the AP exam. So I recommend using that one. One last thing to note about the ideal gas law, it's called ideal for a reason here. So we say that this is for what we call quote-unquote ideal gases, which is pretty much all gases, most of them. We'll talk more about, hey, what happens when they're not ideal. We actually call those real. But this is for gases when they are, they're about at 1 atm. They're not too far extreme away from that. You can have lots of different pressures, but if they're somewhere around that and they're somewhere around room temperature, which is going to be somewhere around 20 to 25 degrees Celsius. So the ideal gas law works perfectly when you have those conditions. If you start going to extreme conditions, we'll talk at the end of the chapter what does it mean and what actually starts to happen to gases. What assumptions now can we not make, and what adjustments do we make to the ideal gas law? We'll take a look at those things at the end. Okay, we're going to stop right there, having gone through all of our gas laws, ending with arguably our most important one, the ideal gas law. This chapter, guys, we definitely start getting into more calculations, back into the math. So remembering to have units on your answers, and especially throughout your work, can't be stressed more than right now. You want to make sure your units match up. You want to, especially with the ideal gas laws I already talked about, you want to make sure that, hey, your gas constant makes sense with your other variables in terms of their unit. You don't want to get any of them mixed up. You want to make sure your answer has a unit on the end. Look for all sorts of information, right? Gas laws, calculating them is actually very, very simple. It's some basic algebra. But the hard part is reading the question and understanding what law do I need to use, what information am I given, am I dealing with multiple gases, am I dealing with one gas? It's all about reading the problem. That's half the battle, or more than half the battle. Once you sort of identify, hey, I've got this information, I can use an equation, all you guys are more than capable of plugging them into the equation and doing the math. That's not difficult. But understanding what to do to get to that point can be tricky. So the more practice problems you can do, the better. Definitely start going through the problem set for this chapter. Spend the time in class working through the different examples, calculate, and do some more calculations. The more practice you can get, the better. I'll see you guys next time when we start talking about how does density factor in. We'll also start going through different examples together for these gas laws and actually work them into some gas stoichiometry. Get some practice into that.
Made with Doodlecast Pro.